take a minute right now to walk you through your homework sheet and what this will look like, and this is also what your quiz is going to be like. The setup is a table that makes it quick and easy to look at shifts in equilibrium. But you can kind of identify here, make sure you've got your SO2 plus O2 reaction, which is the reaction that we talked about in class. This reaction is divided here by the double arrow that's indicated by this little red blocking right here. So we're going to identify a couple things. We're going to identify first what will happen in terms of the shifting of equilibrium, whether it will go forward or reverse, which we'll identify as left or right. We're also going to identify what the effect of concentration will be. Whatever the thing is that we choose, we don't worry about the effect. We just kind of draw a line there or exit out. Sometimes that will even be blocked out on handouts for you. So if you were to add SO2 to a reaction, so since we are adding SO2 right here, that's going to cause it to react more with O2, cause an increase in collisions between SO2 and O2, shifting our reaction to the right. This is going to start using up all of the O2, so our concentration of O2 will decrease as we are making more SO3. Things that are on opposite sides of the arrow from one another have to do opposite things. So as we are using up our O2, we're getting more SO3. If we were to add more O2, so our O2 is right here, it's on the same side as the SO2. Generally, what's going to happen is the exact same thing that happened in our first example. O2 and SO2 will collide more frequently and will speed up the forward reaction. We'll begin to create more SO3. This will use up the SO2 that's in the system, thus decreasing its concentration. If we add SO3, so be very careful, SO2 and SO3 look kind of alike, but SO3 is this guy over here. If we add SO3, we're going to have more of that in there to decompose, thus favoring the reverse reaction. We're not really worried about what happens to SO3 itself as we're adding it to the system. Because we have more SO3 being put into the system, this is going to be decomposing more and increasing our concentrations of SO2 and O2. Now, I always like to use a little saying, add away. So if we look back at everything we just talked about, when we added SO2, we shifted away. When we added O2, we shifted away, meaning we shift to the other direction in the reaction. We shift to the other side of that arrow. When we added SO3, add away. The reaction that we are favoring is going to determine what happens to concentration. When we're shifting towards something, we're making more of it. The other side of this is remove towards. If I remove SO2 from this reaction, there's less of it available to react with O2. So as I remove SO2, I actually, not really allowing the forward reaction to happen quite as much. So this favors my reverse reaction or causes a shift to the left. So since I'm taking this SO2 out, it can't react with O2 to make SO3. So what really happens is the reverse reaction is favored because the SO3 is still breaking down and giving us SO2 and O2. So the amount of SO2 is going to begin to build up. I don't have any SO2 to react that with. And my amount of SO3 is going to decrease since I can't really make more SO3 since I'm taking SO2 out. If I remove O2, so if I'm removing the O2 right here, the O2 is not available to collide with the SO2 and make more SO3. So again, I'm going to be shifting toward the left. My amount of SO2 will be going up since I don't have anything to react it with. I will be using up my SO3. If I remove SO3, if I'm removing this from the system, it won't be available to break down into SO2 and O2. Therefore, I'm not favoring.
In the building, please call the main office. Thank you.
Sorry. If you're removing SO2 or SO3 from the system, you're actually favoring a shift to the forward reaction. The SO2 is not present to break down into SO2. I'm sorry. The SO3 isn't present to break down to SO2 and O2, but we're still forming SO3. What this is actually causing is we are using up our SO2 and our O2. Since we're removing SO3, we're not going to worry about what's happening with that. So what you should notice here with each of these, if we remove something, we shift towards it. So we just talked about removing SO3. We shift towards it. It's almost as if we're shifting towards it to replace it in the system. If we're removing O2, we shift towards it. If we're removing SO2, we're shifting to the left. We're shifting towards those to replace them in the system. Next, we have to talk about temperature. This also works as add away, remove towards. We need to go ahead and identify our heat term in the reaction. Our heat term is over here. If we add heat or we increase temperature, we're going to shift away. So more heat is going to cause an increase in the rate of decomposition of SO2. So by increasing temperature, we're shifting to the left. Since we're favoring a shift toward the production of SO2 and O2, their concentrations will increase. SO3 will continually be decomposed, will decrease. On the other hand, if we remove heat, so if we decrease our temperature, we are going to shift towards that reaction. Really, you can think of this like the heat's not there to decompose the SO3. However, the SO2 and O2 are going to continue reacting. So in this case, we're going to favor our forward reaction or shift to the right. This will cause an increase in the product of our forward reaction, which is SO3, while our SO2 and O2 are being decreased. The SO3 is not breaking back down and creating those. Last but not least, we're going to talk about pressure. Pressure is a little bit different because we have to talk about our moles of gas on either side of the reaction. On this side of the reaction, we have a 2 here, we have a 1 here, over here we have a 2. So I have a total on the left side of 3 moles of gas. Notice these all have G's in them versus 2 moles over here. If you like to have something a little bit visual, this is kind of your big side, that's kind of your small side over there. So as I increase pressure, I need to shift toward the side that has fewer moles of gas so that things are kind of like crunched together a little bit. So this side over here where the SO3 is my crunched together side. So if I increase my pressure, I'm going to cause a shift to the right. Since I'm shifting to the right, I'm favoring the production of SO3. I'm going to get more SO3 by using up SO2 and O2. If I decrease pressure, I'm going to allow things to spread out. So you can imagine now, moving back in the other direction, allowing things to spread out to the 3 moles of gas. So this is going to cause a shift to the left. And because I'm shifting toward the left, I'm favoring the production of SO2 and O2. So they'll be increasing while SO3 is decreasing.